I've been bored lately, so I decided to visit a fun problem from the International Math Olympiad. To briefly summarize, there is a line L which rotates clockwise about a pivot point P in the two-dimensional space S. When L hits a point, that point becomes a new pivot, and L continues to rotate about this point. If you don't understand this concept immediately, I highly suggest you watch 3 Blue 1 Brown's video, which relates to this problem, and then come back. As I began to play around with the problem, I found something vastly different than what I was trying to prove in the first place. So let's ask the question, does there exist an initial pivot point P in S, such that the union of all possible cycles starting from P result in a completed digraph? To start, let's begin with a simple set of 3 points in the field, which is called S in the problem. Let's put the line L on a random point, and work through all the possible paths it could take. At this point, it's very important to note how we can distinguish different configurations of L from one pivot. In this field of 3 points, there are only 2 configurations. Think of how many ways L can be to the left of some point. Well, L can be to the left of both other points, to the left of one point, or to the left of neither. But notice how being to the left of neither is the same as being to the left of one point, but with the orientation of L being flipped. This sort of symmetry is crucial to understanding the problem, and will be important to note later. Now let's consider the general case. If we start with the line outside of all points, we find that the line travels only along the convex hull of this set of points. To summarize, if we know that there are n points in S, and there are originally m points to one side of L and n minus m points to the other, then this amount of points cannot change on either side. I won't prove this here since it has been proven in other videos and texts, and my aim is not to be redundant. Also, I think it's important to note that in order for L to completely start outside of every other point in S, the initial pivot of L must be on the convex hull. We see that this is true since L forms a 180-degree angle about its pivot, and in order for either side to be outside of every other point, then there must be an angle less than 180 degrees which encapsulates every other point in S from that initial pivot. If it weren't possible to do this, then there would have to be some other point which could surround this initial pivot with 2 other points in S. And if it weren't possible, then we could not form the convex hull directed graph surrounding the set S, since there would be no way for L to have less than 1 point to the right of it, which remains constant as we stated before. Now, with all of this being said, what can we say about the main theorem? Well, let's consider just 2 specific points in S, both being whole points, and the one we start on being the initial pivot. If L bisects m points to the left, and n minus m to the right, we know that once L has rotated into position to collide with our second point, P2, then there also must be m points behind L and n minus m points in front. This implies that, in general, we already guarantee that for all whole points, they must be able to make all permutations p whole to pi for all other points in S. This doesn't account for all permutations involving the arbitrary p whole, but it does for all of the combinations including these points. As for the points not in the whole, we must consider how they behave. Let's be clear first in distinguishing which cycles contain these points at all. For instance, if a point P lies in S such that there is no way for L to intersect it, which means that there is no configuration for L on P such that m points lie behind it, then it will not be in the cycle. L will perform a dance of sorts around this point, and all other points for which this criterion is not met. Sound familiar? Well, this is just like the case for a convex hull outside of S. In fact, we can draw multiple convex hulls for each configuration of L once we have chosen its initial pivot P. Though this isn't a necessary fact for proving our initial theorem, I do believe it helps understand a bit better how the outer points and inner points have related properties despite their differences. Returning to the example before, let's consider all cycles which do contain these inner points. Obviously, P inner can be reached directly by L by simply choosing it to be the first point in front of L in its initial configuration. If we want it to connect with some other arbitrary point, P2, then we must consider the exact partition of points to the left and right of L at this unique position. Now, place L on the initial whole pivot point such that this partition is maintained. The same n to n minus m partition we discussed before. Since L rotates continuously 180 degrees before returning to its initial position, then it must hit this point. Think about it. L must maintain this partition throughout its whole cycle, and this configuration is unique at point P inner. Therefore, when L inevitably reaches this angle in S during this specific cycle, it will be at this point. So now that we have all combinations, how do we get the reverse direction for each point? Well, we have secretly already solved this without really needing to think about it. If the reverse is desired, we simply need to consider the case m plus 1 in front, n minus m minus 1 behind L. Since L will have the same orientation in both transfers, the only difference is where L travels to from there. If L travels backward in transfer Pi to Pj, then it will travel forward in transfer Pj to Pi. Necessarily, this puts a difference of only 1 point in the partition, and thus we can simply start L in an initial configuration differing by a distance of 1 point to the left or right to make up for this lost connection. Finally, we can say that for any configuration S, we can form all connections Pi to Pj with an initial pivot P on the convex hull of S by taking the union of all distinct cycles for all initial configurations of L. So, what is the takeaway from this video? Well, there really isn't one. Not that I can think of anyway. Regardless, I learned a lot by messing around with these ideas, and I hope that you can learn yourself about topics that interest you simply by messing around as well. So, if you're ever bored in lecture, don't feel like you need to force yourself to pay attention. Distract yourself with something mentally stimulating, and maybe you too will find something that interests you and feels worth sharing.